For homework number 4, problem 1, write a Raptor algorithm to calculate the user's estimated marathon pace and starting wave. The algorithm will ask the user for his or her personal best marathon time, first in hours, then in minutes. Given that a marathon is 26.2 miles, your algorithm will calculate and then report the user's estimated race pace in miles per hour, followed by the starting wave. The starting wave is determined by the estimated race pace as specified in the chart below. You may assume that the two inputs provided by the user are non-negative. In order to solve this problem, we'll first notice that we are to have two inputs, referring to the best marathon time. The first input will be the hours, and the second input will be in minutes. We see from the example below that it might be 2 hours and 49 minutes or 2 hours and 20 minutes. Then we are to have two outputs. The first output being the race pace in miles per hour, followed by the starting wave. And the starting wave is depicted in this chart here. So before we get into Raptor, the first thing I'd like to do is see if we can't solve for miles per hour given a best marathon time in hours and minutes. So let's use the example provided. We have a race time of 2 hours and 49 minutes. And one way we might solve this is by first converting this into minutes. So we have 2 times 60 plus 49 minutes. So a total of 169 minutes for the marathon pace. But what we'd like to do is take this 169 minutes in a 26.2 marathon race and turn this into miles per hour for a marathon. So we have a 26.2 mile marathon. We want miles per hour. If we divide 26.2 miles by 169 minutes, we'll need to convert our minutes to hours. So we have miles per hour. So we have 26.2 times 60 divided by 169. If we were to work this out, we'd find that it works out to be 9.3018. So we've seen that we can in fact take two inputs, 2 hours and 49 minutes, and come up with the race pace in miles per hour of 9.3018 miles per hour. But how can we take this specific problem and make it more generic so that we can receive any input? Well, if we look at 169, we'll see that it was simply 2 times 60 plus 49 minutes. And looking more closely at this, what we see is that the only parts that were specific to the particular inputs were the 2 hours and the 49 minutes. If we change these so that they'd be variables, for instance, hours times 60 plus minutes, we would find that in general we could take 26.2 miles and multiply that times 60 minutes and divide that by 60 times hours plus minutes. And in this way I can get the race pace in miles per hour for any input of hours and minutes. So with this in mind, let's get started in Raptor and see if we can't develop an algorithm that will take these inputs and provide the specified outputs. We'll start off by adding our two inputs. The first input will be to get the user's hours. What is your best marathon time? And here we want the hours component. We'll call that variable hours. And the other question, what is your best marathon time? And here we want the minutes component of the time. We'll call that variable minutes. From here, we can calculate the miles per hour using the formula that we developed previously. So we'll set miles per hour to 26.2 times 60 divided by the quantity 60 times hours plus minutes. So now we have two inputs and we have calculated our miles per hour. From there we can use the miles per hour value to identify which wave the user should be in using the table that the algorithm specified. So we'll add our selection statements. And the table says that if the miles per hour is greater than or equal to 10.5, then we will output wave A. If the miles per hour is less than 10.5 and greater than or equal to 9, then we'll output wave B. So there's a couple of approaches that we could take with this. We could say miles per hour greater than or equal to 10 or less than 10.5 and miles per hour greater than or equal to 9. But if you take a look, if our miles per hour is not greater than or equal to 10.5, we travel down the no side of the algorithm, then we know that the miles per hour is less than 10.5. So in other words, this part of our selection, miles per hour less than 10.5, that's always going to be true if we follow this path. So I'm going to simplify my selection and I'm actually going to remove that part, so that now we're just checking to see if the miles per hour is greater than or equal to 9. And again, if we're here, we already know that the miles per hour is less than 10.5. Our output should be wave B. We'll add another selection. And this time, if we're less than 9, but greater than or equal to 7.5. So miles per hour greater than or equal to 7.5. And we'll output wave C. If miles per hour is greater than or equal to 6, but less than 7.5, then we'll output wave D. Finally, if we're not greater than or equal to 6 on our miles per hour, then we are less than 6, in which case we would output wave E. So having implemented the algorithm in Raptor, we can test it using some of the inputs that are provided. So let's try the very first input. We'll say 2 hours. 49 minutes, and we're going to expect miles per hour 9.3018 and wave B. When I look at this, I see that all I get is wave B, and I'm missing the miles per hour, although the miles per hour was calculated correctly. So let me go back to the algorithm and see why it is that I'm missing an output. And as I see, while I did calculate the miles per hour, I did not output miles per hour. So I'm going to output miles per hour here. And that way, regardless of what the miles per hour is, it's going to output it before outputting the wave. So let's try this again. 2 hours, 49 minutes. And this time, it outputs 9.3018 wave B. Let's try another one. This time we'll do the second test case, 2 hours, 20 minutes. And we get 11.2286 miles per hour wave A. It looks like so far my algorithm is working. I could fully test it by testing each one of the boundary cases for wave A, B, C, D, and E, but for now I'll just use the test server and see how it is that we're doing. And it looks like our algorithm is correct on 5 test cases, so at this point we can conclude that our algorithm is probably correct and move on to the next problem.